Welcome back. So let's try to implement the PCA from scratch for image compression, the first main application of the PCA. But let's start by asking a question. How many components we have in an 8-bit image? So if you know binary language or you have any idea about binary language, then you will say if we have bits, right, we have zeros and ones. So if we have 8 bits, then we have how many values inside this 8-bit image? We will have 2 power 8. We have 2 power 8 combinations. So we have 2 power 8 values, or we have 2 power 8 components. So we will basically have 256 components in an 8-bit image. And an 8-bit image is a very small image. It's not that large. And as you can see, we have too many components, right? So we will see how we can use PCA and implement the PCA from scratch for image compression. So the first function we need to implement is the SVD, the singular value decomposition, right? Because in image compression, we assume that each column of the image is a feature. And image is basically a matrix, right? So this is the assumption we are making. The input for this function is n by d array corresponding to an image. If we have a gray image, then we will have n by d, right? The number of rows by the number of columns. And for each row column, right, for each value, for each pixel, we can have 256 values, right? And in case we have a color image, then we will have 3 channels. A channel for red, a channel for blue, and a channel for green. Okay, so this function should return the U, S, and V, right? The N by N, the N by D, right? Or N by 1 or D by 1, and D by D, right? For color images, we will have all this times 3. So if you go back here, you will see that this is the dimension we discussed before, right? This is the same dimensions we discussed before. So how we can do so? How we can implement this function? First, we need to get how many dimensions we have. So if we get the shape of X, right, this will return either 2 numbers or 3 numbers. So if we get the length of this list, we will know how many dimensions we have. So if we have a gray colored image, we will have, let's say, 256 by 256. So the length of this list will be 2, so we have 2 dimensions. And if we have a colored image, it will be 256 by 256 by 3. So if we get the length, we will have 3, right? So if we have 3 dimensions, what we are going to do is that we are going to use numpy, right? And we are going to use a transpose function inside numpy, right? So we give it the original matrix, and what we are doing here is that we are transposing the image for broadcasting. So if you go back to the numpy section, you will see that we are discussing broadcasting, one of the main concepts in numpy, right? So you will transpose the image in order to have first the dimensions. So we'll have 3 times 256 times 256 instead of 256 times 256 times 3, right? So this is what this transpose function is doing. Because we need to have the channels or the dimensions, what I mean by the dimensions here, the RGB dimensions. We need to have them at the beginning as the first dimension in order for the next function to work properly. Okay, so what is the next function? We are going to call numpy, and inside numpy you will see that we have something called linalg. So this is the linear algebra numpy functions. Okay, so we have so many functions inside this submodule. Okay, so we have so many functions. We have functions for multiplying the matrices, multiplying the vectors, decomposition, matrix eigenvalues, norms and other numbers, solving equations and inverting matrices, exception. So we have so many things inside the linear algebra module. And the most important one here is the SVD. So this is the singular value decomposition function. And when A is a 2D array, it's vectorized as U NB dot diagonal S at VH. And all this is not really important for you. What you need to know is that there are 2 important parameters for this function. First, A, the matrix itself, we want to have the singular value decomposition for, and the full matrices. right? So the full matrices is either true or false. It's a Boolean parameter, and if true, then U and VH will have the shapes ... so 3, 2, 4, whatever, how many channels we have, times M times N, and 3, 2, 4, whatever, times N times N. Otherwise, so if we choose this full matrix or full matrices to be false, then we will return these matrices without the full matrix, right? So what I mean is that if we go here, if you see here, you will see that, for example, here we are having another column, right? We are returning here an additional column, right? All zeros. But originally, if we want to return the correct covariance matrix, we will return only this, right? The first 3 rows and the first 3 columns. But now we are returning 3 columns and 4 rows. So this is basically in order for multiplying them together. So that's why we can have full matrices or not full matrices. So if we have full matrices, we will return something like this. If we say that full matrices is false, then we will return only the first 3 rows, right? So this is basically how this function works. So it will return U, S, and V. And in case we have 2 dimensions, so if we have a gray colored image, then we will not do this step, we will not do the transpose step, and we will just call this function at once, okay? And we will return the U, S, and V. So this is a very, very straightforward function. Now, in order to rebuild the K components using SVD, what we are going to do is that the inputs for this function are U, S, V, and of course K, the number of components we want to build. And it will return X rebuild. So what we want to return is the reconstructed image using only the first K components, okay? So it should return N times D. So the original X was N times D, and we want to rebuild the image using only the K components, right? Now, how many dimensions we have? The length of U dot shape, okay? So if the number of dimensions is 0, then segment U is basically the covariance matrix, right? So how we can compute the covariance matrix? We will just create numpy zeros array. So we will have, if we have 3 dimensions, it should be numpy.zeros, and we have 3 channels, right? This is the first dimension, and then we have U.shape1. So U.shape1 is basically N, right? And V.shape1 is basically D. So we need to have the new sigma, right? N times D, okay? So this will create an empty matrix with a size N times D. And then what we are going to do is that we are going to fill this covariance matrix. From where we are going to fill this covariance matrix? From S, right? If you remember, S was the covariance matrix, right? This covariance matrix. But now we want to build the full matrix in order to build the image. So we are going to build a matrix with all zeros, and then we are going to fill the diagonal with the values in sigma, right? Sigma is originally this one, because we returned not the full matrix. We returned only the 3 by 3. So we are going to build a new matrix, all zeros, with this shape, right? And then we are going to fill the diagonal with the values of sigma. That's exactly what we are doing here. As you can see, we are filling the diagonal from numpy, and which matrix we are filling? We are filling sigma nu, which is all zeros at the beginning. From where we are filling this matrix? From S, right? And as you can see, for J in range 3, because we have 3 dimensions, so we are going to do this for the first dimension, the second dimension, and the third dimensions. For how many Ks, right? For how many components? For K components. So that's why you can see here, we have here from 0, right, to K, okay? So we want only the first K components. So we will fill the diagonal, but not all the values in the diagonal. Let's say we have 3 dimensions and we want to get the first 2 components, okay? So we will return this one and this one. Why? Because this one will correspond to the largest eigenvalue, and this will correspond to the second largest eigenvalue, and so on, right? So we want to return from the very beginning till the K column, okay? So this is basically how we are going to do it. After we do so, we will build X. How we are going to build X? This is by performing matrix multiplication. So how we are going to do this again? We are going to multiply sigma, right, times v, and then the output of this will be multiplied by u, right? This is the singular value decomposition, right? If you check here how we compute x, we compute x by multiplying sigma times v, and then all this is multiplied by u, right? So you might say, but we have a transpose here. If we use numpy matrix multiplication, then this is all have been taken care of, right? Because here v is actually v transpose. What we return from here is v transpose. We are not returning v itself. Okay, so this is basically how it works. This is how we will build x again. And if you remember, at the beginning we built x, or we transposed x, by having the first dimension to be the channels, and then the second dimension the number of columns, and then the number of rows, right? We want to do the inverse operation of this transpose, right? So how we are going to do this? By using transpose again, and then we want to have 0, 1, and 2. So the first dimension will be the number of columns, the second dimension the number of rows, and then the third dimension should be the number of channels, or RGB. Okay, so this is how we build x again. Now if we have only 2 dimensions, we can do this step without 3. We can have 2 here, only 2. We can build sigma nu just like this, but numpy.zeros, and we won't have this dimension. We will have only 2 dimensions, and then we will do this step. We don't really need to fill the diagonal using iterations. We can fill it in one line, and we don't really want the transpose here because the matrix is correct, right? The x is correct. So we can do this, or we can just do it in one step. So we are multiplying v by s by the matrix. We are multiplying the v, right, by the diagonal of s by the u matrix. And we are doing this for all values, right, until k, right, until the k's value. So this is basically how we can rebuild x for image compression, right? So it's very, very straightforward. Now we want to compute also another thing called the compression ratio. Okay, so this is very, very important. If we are compressing an image, we want to know what is the compression ratio. So the compression ratio is basically the number of stored value in the compressed image, right? How many kilobytes, let's say, how many pixels we have in the compressed image, over how many values, right, or numbers stored in the original image. So this is the compression ratio. So how we can do this? Very, very simple. We have an equation for this. It's basically n, right? N is the first dimension of x, x.shape 0, over 2 times k plus 1, right? So you might say, no, it should be n over k. We don't really want to have n over 2k plus 1. Why the 2 and why the 1? There is some details about this which you can check in this PDF, right, in this lecture, and you need to go to page 12 to check this, because it can take a while, and honestly I want to focus on the most important things. But you are free to check this source and send me a message or write a question in the Q&A section, and I will be happy to answer you, right? But there is a reason for why we have 2 here and why we have 1 here for the compression ratio, okay, with an example. So you will find an example in the PDF, right? So this is how we compute the compression ratio. After that, we want also to know how much variance did we preserve, right? Because this is very, very important. If we didn't really preserve that much variance, then the PCA is not actually doing a good job, right? So we want to compute the proportion of the variance in the original matrix recovered by rank k approximation. So if we use only the first k components to reconstruct the original matrix, the original image, what is the variance? How much variance we preserved, right? So how we are going to do this? We are going to use only sigma, only the covariance matrix. We don't really want the other 2 matrices, and we want k, right? So the recovered variance will correspond to just a number, right? So the number of dimensions of S can be either 1 or 2. So if we have 2D image, then the number of dimensions will be 1. If we have a 3D image, then the number of dimensions will be 2, Why? Because S itself is basically the minimum of N and D times 1, so we have only one dimension in case we have a 2D image, and it will be the minimum of N and D times 3, so we'll have 2 dimensions for colored images, right? So we will have a 1 value for each column. So how many columns we have? We have 256 in a 8-bit image, and in case we have a colored image, it will be 256 times 3, because we have 256 for red, 256 for blue, and 256 for green. Okay, so let's see how we can compute the recovered variance. We will compute the eigenvalue first, because as we said, we can compute the eigenvalue from the covariance matrix, right? And we can do this just like this. We will do this step, right? S times 2, so basically S power 2, right? So each value in S, okay, we will get the square of this value. And then we will divide by S dot shape 0, so basically N or D, minus 1. So this is how we can calculate the eigenvalues. In case we have one dimension, then the eigenvalues, this variable will contain 256 values, right? The 256 values are basically S squared over, so each value in S, each value in the covariance matrix will be squared, and then we divide by the number of values we have in this matrix or in this vector. Okay, and then we are calculating the significance. Okay, and how we calculate the significance? So the significance is basically the importance of each eigenvalue. So this can be a little bit tricky, but actually it's very, very straightforward. We are going to loop over all the eigenvalues, right? So for I n eigenvalue, what we are going to do is that we are dividing nb dot absolute I. So this will return the absolute value, because the eigenvalue can be negative, so we don't really want this to influence our decision or our decision for the influence. So what we are doing is that we are dividing the absolute value for each eigenvalue over the summation of all the values, right? So basically this should be, if we sum all the values here, it should be 1, right? Because here we will have, let's say, let's take a look at an example. Let's say for the eigenvalue it will contain, let's say 0.2, 0.3, and then 0.5, for example, right? So what we are going to do is that for the first value, or let's say instead of having it that easy, let's say 0.4, 0.3, and 0.5. Okay, so for the first example, the first value here will have 0.4 over the summation of this and this and this, 0.8, 1.2, right? And then we will have 0.3 over 1.2, and then 0.5 over 1.2. So this is basically the new list. It will contain these values. So this is basically how we can compute the significance of each eigenvalue. And if we have a negative here, then it will be a positive here, right? Because we are taking the absolute. And then after doing so, after getting the significance, we will sort them in descending order, right? So we'll use the sort function in the lists, and we will use reverse equal true to sort them in ascending order, because by default this function will sort them in ascending order. Okay, after doing so, we are going to sum the significance of these values, right, of the eigenvalues till k, so from 0 to k, right? Add all the significances till the k's component, right? So this is how we basically compute the variance, how we compute the recovered variance. We compute the recovered variance from the eigenvalues, we normalize the eigenvalues, we sort the eigenvalues, and then we sum these values from 0, from the first index till the k's component, right? So this is how we compute the recovered variance. And there is also another way we can do it, right? Just like this, the first step is exactly the same, and then we can calculate the total variance by just summing the explained variances, and then the recovered variance is basically explained variance over total variance, and then we will get all the values till k, right? So this is the same as this one, right? So the explained variance, the recovered variance. Now this is how we can do it if we have one dimension in case of a 2D image. Else, so if we have 2 dimensions for S, so basically a 3D image, then we are going to do the same exact steps we did before, but for range 3, right? We are going to do this for I. So we are going to do this for each single dimension, because we will have S, as we said, 256 by 3. So we'll have 3 channels. So we are going to do this for R, G, and B. And we will return the recovered variance. Now let's test the code in order to see if it actually works, right? So here we have a cat image, right? So if you check it here, this is the image we have of a cat, right? And what we are going to do is that we are going to use CV2. So this is short for Computer Vision 2. This is a library for reading images and so on, but we can do it also in Matplotlib. But this is much easier if we want to convert from RGB to gray or the other way around. So we are going to read the image using PLT, using Matplotlib, and this import should be at the very beginning. So I'm going to do this after the video, but this should be at the imports at the beginning, right? Now after that, we are going to use from CV2 a function called CVT color, convert color, and we are going to convert this image to color BGR, right? Blue, green, red, to gray. So this will convert the image to a gray image. And then we will subtract the mean, so we will get the mean of this image, right, of the blue-white image, and then we will subtract the mean just like before, and we will use our implementation of the singular value decomposition, which will return U, S, and V. And we have here a list containing the number of components we will use to rebuild the image. So we will try to rebuild the original image using 1 dimension, 2 dimensions, 5 dimensions, 10 dimensions, until we reach 256 dimensions. So we will build the image with all the dimensions we have. So let's do this. First, we are going to loop over all the components, all the lists, right, all the elements in this list, and we are going to call the rebuild SVD, right, the function we implemented with the U, S, and V, and of course the K. So this is the image after we rebuild it. And we are going to use the function called compression ratio. We will give it the image and the number of components, and this should return C, right? And we just want to round the numbers in order to not have a very long float for better visualization. And we'll have R, which will correspond to the recovered variance proportion. So we will give it S and K. And then we will have subplots, right? And we will have 9 subplots, because we have here how many? 1, 2, 3, 4, 5, 6, 7, 8, 9 images, right? 9 rebuilds of the image. So let's run this code and see what we will have. So as you can see, if we rebuild the image, the black-white image, using 1 component, you can see that the image is pixelated, right? So the compression ratio is 85. So this means we compress the image 85 times, right? So this is a very large and severe compression. But at the same time, the recovered variance, the proportion of the recovered variance, is only 42%. So most of the variance is not really recovered. So this is a problem, right? And we can see this. We see that we cannot really interpret anything from this image. So most of the useful information is gone, right? So as you can see, we have some pixelated values here, pixelated values here, pixelated values here. So what we have done is that we have taken each 256 pixels and we assign only 1 value for these pixels, and then we take the next 256, assign 1 value, the next 256, assign 1 value, and so on and so forth, right? So using 1 component, when we build the complete image using 1 component, it's not that clear. But if you check with 2 components, it starts to get a little bit, we can see some patterns of the image, right, of the cat, right? So here we have the compression ratio 51.2. So this is also a very large compression ratio, and recovered variance is 61% using only 2 components. But starting from 5 components, we can really see the image, right? We can really see the cat. So using 5 components, 10 components, even 20 components, so starting from 20 components, the pixelation is very unnoticeable, right? And at the same time, we compress the image more than 6 times, right? So this is a very plus. So this is a very positive thing we can do. Using only 2 components, we can rebuild the cat image and we can rebuild it with high accuracy, and we didn't really lose that much information because we recovered 92% of the variance in the image, right? So maybe some information here is not that clear, but other than that, all the information is here, right? And we have here 40 components, 80 components, so you cannot really see any difference whatsoever between 80 components and 256 components, right? There is a huge difference in the number of components, but at the same time you cannot really notice any difference, right? So we recovered 99.2 of the variance, and we compressed this image 1.5 times, right? And using all the components, as you can see, the compression is almost 0.5, so it's like we send the image twice if we used all the components. And you can check this in the resource I left in the previous lesson. Okay, so this is basically how we can do it for the black and white images, right? We can do the same for the colored image. So if you check the colored image right here, you will see that also using 1, 2, or 5 components, it's not that clear, but using more than that, the image starts to be more and more clear. So using 40 components is almost the same as using 256 components, right? So look at the full image here, and you'll see that there's not that much difference between this and this. So there's a recovered variance for each component, for R, G, and B. Okay, so this is basically how we can visualize this, how we can implement the image compression ourselves. And in the next lesson, we will compare our implementation with the sklearn implementation. So we can do all this using sklearn in a few lines, but of course, doing it from scratch can help you understand the concept much better. So in the next lesson, we will see how we can compare our implementation with the sklearn implementation. So let's go to the next lesson.